Yeah, welcome everyone to the Theory of Machines class. Just to give introduction, my name is Mithilesh, and I am a mechanical engineer. Uh, then I did masters from IIT Delhi in engineering mechanics, and I'm working in the field of mechanical engineering from last 6 years. Okay. Yeah. So coming towards this GATE exam, I have given it in 2014, and yeah, after that I taught this subject, I think around 4 or 5 times. Yeah, and this time I'm teaching you guys, so I welcome you all. And in today's class I will just give a brief introduction, what are all the topics we have to study in this subject, and we'll start with the first topic. So with this introduction, from GATE point of view, if you see this theory of machines, including vibration, comes for around 8 to 9 marks. Yeah, if you look uh, the weightage of previous year papers, in some cases it went to till 13 as well. In some cases it was like 5 to 6 marks as well. But on an average, we can expect around 8 9 marks questions will come from this subject. Okay. So I'll be teaching you only the uh, part excluding the vibration. Okay. Some other teacher will teach you vibration. I'm not sure whether it started or not, but I'll be teaching you these topics only, which I have mentioned here. So for your syllabus, you have displacement, velocity, acceleration analysis of the plane mechanisms. So in order to understand this, first we have to study the different mechanisms and machines. So our today's session is fully dedicated to understand the different mechanisms and machines, and from the next class onwards we'll go into the details of this. Then we have dynamic analysis of the linkages, cams, gear and gear trains, flywheel and governors. Then we have balancing of reciprocating and rotary masses and gyroscope. Okay, so these are the topics you have for your syllabus. And in today's session, our focus is mainly on understanding the machines and mechanisms, uh, which will act as a basic knowledge for understanding the first topic, which is displacement, velocity, and acceleration analysis. Okay. Yeah. Before we proceed, if you have any doubt or questions, feel free to ask. Okay. So after every slide, I will ask you guys um, whether I should proceed or not to the next slide. So what I will expect response during that. Okay. So whenever you are done with this slide, I'll go to the next slide. And if you are still writing, feel free to put a message in our chat box. I will wait for you. Okay. For this subject, you can refer the SS Ratan book. Okay, it's a very good book. You can refer that, and for practice, you can just solve the previous year questions. That will be enough. Okay. So yeah, SS Ratan book. I think you'll be easily able to get the soft copy as well. If you don't have, you can just Google it. I think you'll get it. But if you are still not able to find, I will help you with. with that. Okay. Okay. Can I proceed to the next slide? Okay. So in today's class, we will study mechanisms and machine. Okay. So there are two new words here now. One is a machine and another one is a mechanism. Okay. Machine. Let's look into the definition of it. The definition will help us to understand uh, this understand in very detail. Let's try to understand the definition. So machine can be a mechanism or a combination of mechanism. Okay, which apart from which apart from imparting definite motion to the parts, also transmits and modifies available mechanical energy available mechanical energy into some desired work, into some kind of desired work. Okay. So in order to understand the definition of machine, we should know first mechanism, because in the machine definition, the word mechanism is used. So I would like to introduce that first, mechanism, and then we'll come back to this definition to understand it in detail. Uh, Mechanism is a combination of rigid bodies, combination of number of rigid bodies, uh, number of bodies which are usually rigid. Okay, assembled in such a way that assembled in such a way that okay, I think my screen share got ended. Let me see the issue. Okay, I'll read the definition in the meantime. Combination of a number of bodies, usually rigid, assembled in such a way that the motion of one, the motion of one causes constrained and predictable motion of others. Okay, try to understand. So we have like couple of rigid bodies. We are assembling them in a such a way that if we are giving motion to one, okay, it will cause a constraint or predictable motion of others. Okay, I'll come back to this slide. um, Before that, I'll just give one simple example of this uh, um, slider crank mechanism. Okay, or let's take this reciprocating engine, which is we know that in the reciprocating engine we have piston cylinder arrangement, and piston is connected to through this connecting rod to the crank. Okay, so if it is a IC engine, then we are converting this reciprocating motion into a rotary motion. Okay, so basically this crank, this connecting rod, this piston, and the overall frame, they are nothing but the bodies, rigid bodies, you can say. Okay, I'll come to the definition of rigid bodies later, but as if now, try to understand them. These are the bodies which are rigid, and if you rotate crank in certain direction, accordingly the connecting rod will rotate, and accordingly the piston will move. Okay, if you rotate it is counterclockwise, at if you consider this position, then piston may come backwards, and if you rotate this clockwise, then piston may move in a forward direction. Okay, so this is similar to what we are studying here in this definition. Okay, so I came to the previous slide now. uh, what we said here, it's a combination of number of bodies assembled in a such a way that motion of one causes constrained and predictable motion of others. Okay, so we have seen, like in slider crank mechanism, which I shown, if you, for example, if you rotate the crank in clockwise or counterclockwise, from that position the piston either will move in forward direction or backward direction. Okay, so and connecting rod will also move in the predefined or predictable motion. Okay, so this is one of the simple example of mechanism, and in this chapter we are studying different types of mechanisms. Okay, and what is machine? Machine is either a mechanism or combination of mechanism. So what could be the combination of mechanism? Just take the same example. Now this is, in this case, it is just a slider crank mechanism, but if I put some, let's say, wall mechanism here. Okay, so let's consider it as an IC engine. You will put some walls, and these wall levers you are again connecting to the crank shaft. Okay, at appropriate location. So then this lever mechanism, again you are adding to the slider crank mechanism, right? So IC engine, you can say, is a not just a single mechanism, it's a combination of mechanism, right? So we have an inlet wall, outlet wall, and these walls are connected through a wall mechanism. Okay, so which will open and close the wall depending on which stroke of the engine is ongoing. Okay, so IC engine, internal combustion engine, is a good example, you can say, for a machine where we can clearly see that there is a combination of mechanism which, apart from imparting some definite motion to the part, so here not only just bodies are moving, but what is happening here, it also transmits and modifies the available mechanical energy into some desired work. So what is happening here? Basically we are converting this reciprocating motion into the rotary motion. So it's in case of IC engine, our desired output is rotation. Okay, we want our wheels to rotate. So um, how we are converting the rotary motion into the, sorry, reciprocating motion to the rotary motion is by using this IC engine. Okay, so this IC engine is a machine which is helping us to convert the one form of let's say available mechanical energy into some desired work. Okay, I hope the definitions are clear to you. Any doubt till this? Yeah. Okay, so this example which you is an IC engine where we have maybe you are converting reciprocating motion into a rotary motion. Okay, the same mechanism you can think for a compressor. Okay, or yeah, compressor, for example, where um, you are actually converting the rotary motion into the reciprocating motion. The same mechanism can be used for it. Okay. Okay, so for example, this mechanism not just fitted for the IC engine, but you can use this is same mechanism used in reciprocating pumps or reciprocating compressors. But thing is that the input in that case is rotary motion. Okay, and you are converting it into the reciprocating motion. Okay, so it's just opposite of IC engine. Okay, so so if I want to draw a simplified version of this diagram, how it will how it will look like is this. Let me try to draw a simplified version of this mechanism. Okay, so this is the crank. Okay, then we have the connecting rod. Okay, and this is the piston. Okay, so this is your link number one. Okay, link number one in this case is, you can say, a frame or the support system on which this mechanism is mounted. Link number two is the crank, which is having a rotary motion. Okay, link number three is a connecting rod, and link number four is a piston, which is um, having a translatory motion. Okay, so this is a simplified diagram of the this mechanism, I would say. Okay, so here this 1 2 3 4, these are, I'm saying it as a link. It means the same thing what we have studied till now, that is rigid bodies. These are the rigid bodies. 1 2 3 and 4 are the rigid bodies. Rigid means non-deformable bodies. Okay, so let's try to understand first some definitions. At this point, it should be we need to understand what are these different links, how we form the pairs, what are the rigid bodies, what kind of motions mechanism can have. Okay, and what kind of pairs um, will form when you attach links. Okay, so all these things we have to study first. These are some basic definition which are required in order to understand any mechanism in detail. Okay, so we'll study some definitions now, little bit theoretical topic. Okay, but that these topics will help us to understand the mechanisms in detail. Okay, because once it is clear, then if you study 4-bar chain, single slider crank mechanism, double slider crank mechanism, then things will be more clear. Okay, so with that, let's start with some basic definitions. I have kept some figures ready in order to save time. So first topic which we have to study is a type of constrained motion. Okay, there are three types of constrained motion. One is completely constrained motion, second one is incompletely constrained motion, and third one is successfully constrained motion. Okay, I'll repeat. There are three types of constrained motion: completely constrained motion, incompletely constrained motion, and successfully constrained motion. So let's try to understand them one by one. Take this example: completely constrained motion. Completely constrained motion. Okay, whenever the motion between the two elements of or two bodies, you can say, is in definite direction irrespective of direction of force applied. Okay, So for example, let's take this first example, figure number A, okay, where you can clearly see we have a square prism, okay, which is sliding in a box having a square hole, okay. So in this case, whether the this square rod or prism, will it rotate inside that box? No, right? It will just slide inside the box. Okay. So even if you applied any load in this direction or this direction or any this direction, it will just slide. Okay. It will just slide. Okay. If you are applying force from left hand side at any particular angle, it will slide. It will try to slide in rightward direction. But if you apply some loading in left direction, like let's say from right towards left at any angle, this prism will try to slide in left hand side, okay, in this backward direction, for example. So basically it will just slide irrespective of direction of force which you are applying here. Okay, so if you even if you try to rotate it, it will not rotate. It will just try to slide only. Okay, so this is an example of completely constrained motion. I'll repeat the definition. You can write when the motion between two elements of pair or motion between two bodies is in a definite direction irrespective of direction of force applied. Okay, so motion is in definite direction irrespective of the direction of the force applied. Okay, similarly in the second example, um, figure B, there we have a cylindrical rods in the cylindrical hole, but that rod is with collars. So these are the collars. So if collars are not there, then in that case that rod can either translate or rotate, correct? But if collar is there, then this motion is not possible now. Do you agree? Only only rotating motion will be there. Is it clear? So basically what we are doing is we are completely constraining the motion in one particular direction, okay, by some means. Like in first case, we made that hole in square shape, and our the prism is also in square shape, so it will have only sliding motion, and we can make sure that it will not rotate. In the second case, if you don't put the collars, it will either slide or rotate depending on the force applied. But if you put the collar, we are actually uh, making a definite direction motion irrespective of force applied. So we are completely constraining the motion in rotating direction only. Okay, so these are the two examples to understand that irrespective of direction of applied force, the motion is in particular or a definite direction. Okay, can I proceed towards next slide? The second type of constrained motion is incompletely constrained motion. Yeah? So it's just opposite of what we have studied before. In completely constrained motion, the motion between two element of the pair is in definite direction irrespective of force applied. And whereas in case of incompletely constrained motion, the motion between the two elements of the pair is possible in more than one direction depending on force applied. Okay, so motion is possible in more than one direction and depends on force applied. Okay, so here the example is cylindrical shaft in a cylindrical hole. It can either translate or rotate. So if you apply force or torque, it will rotate. If you apply horizontal force, it will translate. So depending on the force applied, okay, depending on the direction of force applied, okay, use the word direction. Depending on direction of force applied, the motion can either be sliding motion or rotating motion. Okay. And the last one is successfully constrained motion. So here, whenever the motion between the two elements of the body is possible in more than one direction, but it is made to have one motion only in one particular direction, okay, then in that case, you can say it as a successfully constrained motion. Okay, so for example, if you take this example of shaft in a four-step bearing. Okay, so maybe you might have studied the different types of bearing in machine design. So uh, so this is a footstep bearing which we have, and you can clearly see the shaft is cylindrical. Okay, and it is free to basically rotate and do translation motion inside this bearing house, either in so it will either rotate or move up and down. But because of some external force or external means, in this case the force which we are applying here in footstep bearing will be always uh, the axial force. Okay, so we can call it as a thrust bearing as well, and which causes it to move only in the direction of translation motion. Okay, so it will just move up and down. So indirectly, though the motion is possible in more than one direction, but but it is made to have motion only in one direction because of some external means, then in that case we call it as a successfully constrained motion. Okay, similarly, if I give another example of piston cylinder, which I have drawn in on the second slide. Piston is uh, piston cylinder in a internal combustion engine. What it can either rotate or it can translate, right? Because it is a cylindrical rod in a cylindrical hole, but it is not rotating inside the IC engine. It is just translating in the IC engine. Why? Or inside the cylinder, because of the external constraint. Okay, so we are constraining the piston with a connecting rod and crank to have motion only in the horizontal direction or only in the reciprocating direction, not in the rotation. Okay, I hope you understood um, all these three kinds of constrained motion. Any doubt till this? Yeah.
So in slider crank also the piston was not rotated because of the constraint also.
Yes, correct. Rather than slider crank, yeah, you can say any, like for example, um, reciprocating pump, reciprocating compressor, or IC engine. In that case, piston just uh, do the reciprocating action, not the rotary action. Okay. Can I go to the next slide? Yeah, thanks. So Yeah, as I already mentioned, we should know this rigid body definition. So what is rigid body? What is rigid body? Rigid body is that body, um, or we can say a body is said to be rigid under action of forces if it is not distorting, or if it is not uh, deforming under the action of forces. Okay, it's not deforming under the action of forces. Okay? Then we call it as a rigid body. So what is meant by not deforming? So if you take any body and if you're applying a load, let's say if you to take any two points in that body, whatever is the distance in between these two bodies before and after applying load, if it is same, then you can say that uh, the body is not deforming. Okay, I'll repeat the definition. So distance between any two points I'm saying. Okay, uh, if it is like not just these 2 points, you can take like these 2 points. Okay, so if distance is not changing, then that body is rigid even if you applied the load. Okay, and what is resistance body? What is resistance body? What is the resistance body? Can anyone tell me when we say a body has a resistance body? uh, yeah, it is deformable. It's not rigid body, but it is rigid for the purpose it has to serve. Okay, yes, yeah, correct, like ropes or belts or fluid. These are the examples of resistance body. So what is the definition? Bodies which are rigid for the purpose they have to serve. Okay, so for example, if I give you let's say um, uh, we can take an example of, let's say, fluid is incompressible, right? So if you take a liquid and you try to, let's say, compress them in a hydraulic press, so basically it will not deform in a hydraulic press. How the hydraulic press will look like? Maybe let's say something like this. Okay, and from here if you are applying some load, and let's say here if we have another piston, let's say if whenever you applied load, okay, so accordingly the motion here will go up. Okay, or this platform will move depending on how much you are compressing from the left hand side. Accordingly the movement is there in on the right hand side. So basically in this case, this fluid which is inside this hydraulic press, we can say as a resistant body. Okay, under the action of compressible load. But if you, in general, if you see, fluid can take any shape, size, if you depending on where you are putting them. So in that case, the first definition of rigid body will not be correct because it will deform. But under particular some let's say purpose, for example this one which I have explained you just now, that is, if you use the fluid in a hydraulic press, then in that case it is behaving like a rigid body. Okay, then you can call this as a resistant body. Okay, similarly if I take example of belt, belt drive. Okay, so belt drive over the pulley. So let's say if it is moving in this direction, okay, then this will move in this direction and this direction, for example. Okay, so belt is a rigid body when you subject it to the tensile forces, but in general, let's say if you apply some other loading apart from tensile, like in that case you can clearly see belt is like a flexible and it is not like a rigid body. Okay, any the distance between 2 points may not be always same if you apply any other loading, like maybe for example compressive loading or something like that. But in case of tensile, we know that we are maintaining, so for example whenever they are mounted on this pulley, if you draw the free diagrams of this, these belts are under the action of tension, and for this purpose they are acting as a rigid body. Hence you can say this is also a good example for the resistant body. Okay, is it clear till this? Yeah, correct. So basically they deform, resistant bodies are there, the ones which will deform, correct, but under the some particular, let's say, purpose, when you use it for some particular purpose, they are, if they are behaving like a rigid body, then in that case you can say them as a resistant body. Yes, relative velocity was zero. Yes, you can say that for rigid body definition, like if 2 points, in between 2 points distance is not varying, then the relative motion velocity is also zero in that. Correct, but simplest example would be this, like they are not deforming means the distance between any 2 points before and after application of force, if it is remaining same, then you can call it as a rigid body. Can I move towards next slide? The basic element for making a mechanism is a link. Okay, link is nothing but a rigid body, or you can say a resistance body, um, with some rigid connections between them. Okay, so a link can be a binary link, tertiary link, and quaternary link. Okay, depending on how many connections it can make. Okay, so in the example of slider crank mechanism, this was our crank, and you're connecting, you're attaching the connecting rod to it, correct? So this is, let's say, link number 2 and link number 3. Then we have you're fixing here to the link 1, and we have piston, which is link 4, and which is again kept on a frame 1. Okay, so these all are links basically. So we have a piston, which is fourth link in this mechanism, connecting rod, which is third link in the mechanism, crank, which is second link in this mechanism, and the overall frame is, or support system is first link in this mechanism. Okay, so basically link is not, or is you can say a rigid body or a resistance body or a group of resistance body with a rigid connection preventing their relative motion. Okay, so this point, so um, if you take a link, for example this binary link, in between these any 2 points, if I consider this point here and this point here, in between these 2 points the distance will not change over the time. Okay, or even if you apply the loading also, even if you apply loading, the distance between these 2 points is not going to change because link is a rigid body or a resistant body. Another way to define the link could be like a member. Okay, so um, of a mechanism. So 1, 2, 3, 4, these are the members of this mechanism, and they are just connecting to each other to have some relative motion between them. So for example, if you, depending on how you rotate this, we will decide how the link 3 and link 4 will move. Okay, how the link 4 and link 3 will move. So basically links are nothing but rigid bodies, and they are members of the mechanism, and they are connected to each other to have some relative motion between them. Okay, so you can call this link, so you might have studied some names like kinematic link or element, all are same. Okay, you can call it as a kinematic link, you can also call it as element, or you can call it as just link. All the terms are same more or less. Okay, nothing is different. The links can be binary as I shown here. It can be tertiary or it can be quaternary links, depending on the how many connection it can make. Okay, um, so here in binary link you can just connect at one location and two locations. In tertiary link connection can be made at three locations, whereas in quaternary links you can make connection at four different locations. Okay, and I have also given you example of this single slider crank mechanism, where link number one is like our frame and guide ways, two is the crank, connecting rod is three, and slider is fourth link. Okay, is it clear about the link, definition of link? Yeah, then let's try to understand the how you will form the pair. Okay, so for example, in the same, in this slider crank mechanism, the link 1 and 2 is paired. Okay, or it's connected. Similarly, link 2 and 3 is also connected. Link 3 and 4 is also connected, and link 4 and 1 is again connected. They are forming one kind of pair. Okay, either let's say turning pair or sliding pair, or there can be some other types of pairs also, depending on let's say what kind of contact we make, what kind of mechanical constraint we are putting, and what is the nature of motion between these two links. Okay, so with that heading, just write down that kinematic pair. Write down heading kinematic pair. Kinematic pair, you can say, is a joint of two links. Pair means joint of two links. Joint of two links having some relationship, having some relative motion between them. Having some relative motion between them. Okay, so kinematic pairs are of three type. First type is depending on nature of contact. Kinematic pair types depends on or classified according to the first nature of contact. Depending on nature of contact, there are two types of pairs. One is lower pair and higher pair. Okay, depending on the nature of mechanical constraint, constraint. Okay, there are two types again, closed and open, and depending on nature of relative motion, okay, there are two types again, sorry, many types. It can be sliding, main are sliding and turning pairs, but it can have rolling pair as well. uh, the links can have screw pair also, or they can have spherical pair also. Okay, so this is the classification of different types of kinematic pairs. So depending on nature of contact, we have lower and higher pair. Nature of contact means if two links, whether they have surface contact with each other or whether they have point or line contact with each other. Depending on that, we have this names, lower and higher pair. In case of lower pairs, we have surface contact. Okay. Okay. And in case of higher pair, we have point or line contact. Okay. So what could be the example here? Let's say cam and a follower. How the cam and follower will look like? Suppose this is the cam and follower is like this, a pointed follower. Cam is turning like this. So you can clearly see there is a point contact between cam and follower. Cam and follower both are the links. Depending on the motion of cam, your follower will move up and down in the guideways. Okay. But in between these two links, what kind of contact you have is point contact. Okay. Similarly, if I take an example of ball bearings or roller bearings, in case of ball bearing, we have point contact in between ball and the uh, bearing races. Okay. If you consider a roller bearing, you will have a line contact between roller and the races, inner and outer races. Okay. So all these examples are of higher pair where we have either point or line contact. What could be the example of lower pair? Can anyone tell me the example of lower pair where you have surface contact between two links? Yes, slider um, is a good example. Then basically any shaft rotating inside the bearing, if you have a shaft and a hole kind of combination, like as you said, slider or shaft rotating inside the bearing, all these are examples of the uh, lower pair where we have the surface contact. Yep. So the first type is nature of contact, that is lower and higher pair. The second type depends on the nature of mechanical constraint. Okay, so I'll go to the next slide now to explain it. I have some diagrams ready with me. According to the nature of mechanical constraint, you have two types. One is closed pair and you have unclosed pair. Okay. See, after completion of syllabus, I will be uploading all the PPTs in some dry location and we will share it to you. So even if in some case you diagrams are difficult to draw, and if you find you are not able to draw it now, no need to worry. These diagrams you can take it from SS Ratan book or any, if you just Google it, you will get these diagrams. Or anyway, I will be giving you all these slides. Uh, okay. Okay, we got a question. How many hours Tom will take? Yeah, I would expect around 25 to 30 hours. Around 25 hours it will take um, to complete your syllabus. Okay. Yeah, some up and down, like a couple of classes can be more than that as well, but around 25 to 26 is the target. Yeah. So how we'll plan is we will go through the concepts first, and and then later on what we'll do is we'll solve some questions. Okay. Uh, yeah, I'm not sure the YouTube where it takes 80 hours, but our plan here is just to teach you Tom, not the vibrations, and I would expect it to um, complete in 25 to 30 hours. If you still find it is fast, you can feel free to comment. Okay, I will slow down whenever you feel I'm going fast. Okay. Yeah. So what I was explaining you is depending on the nature of mechanical constraint, there are two more types, which is closed pair and unclosed pair. So what is closed pair? When the elements of pair are held together mechanically. Okay. In first case, we can clearly see this follower is enclosing the cam. Okay, the cam is inside this follower, and it is like mechanically you can say held together. Okay, whereas in second case, which is example of unclosed pair, the cam and follower are connected just because of force of gravity. We are not forcefully putting follower on cam. The follower is sitting on the cam because of the gravity. They have that contact, or um, they have this pair because of the action of gravity. So depending on how you move the cam, follower will move up and down. But in the second case, in the first case, the difference is that in the first case, your follower is enclosing the cam. Okay. Mechanically, so if you want to separate this cam and follower, it's difficult, you cannot do it. Whereas in second case, if you just take out the follower, you can easily separate cam and follower. Okay. So this is the difference between closed and unclosed pair. If pairs are held together mechanically, then we call it as a closed pair. Okay. And in case of unclosed pair, the they are held together due to force of gravity. Okay, is it clear till this? Yeah. Another type of pair which can form is like according to the nature of relative motion. We have already studied these two motions. If you remember that we have square, sorry, a rectangular or square prism, which is reciprocating inside the rectangular or square hole. This is a good example of sliding pair. Okay, so the first example is for the sliding pair where two links have sliding motion relative to each other. In case of second example, the figure number B, we have the revolving motion related to each other. The circular cross section shaft is uh, rotating inside the circular hole, and with the collars. So we are just constraining it to the turning pair. Okay. So if we have only um, a revolving motion, you call it as a turning pair. Okay. The first one was sliding. Second one is turning. I'll use the same names A, B. Turning pair. C is rolling pair. You can clearly see it is just a cross section of ball bearing. You can clearly see a ball is kept in between the two races, inner and outer race, and in between this recess and ball, we have a the pair which is formed. We call it as a rolling pair. Okay, so they have rolling motion related to each other. Coming towards the figure number D, here we have a screw pair. You can also call it as helical pair. Okay, so when two links are turning as well as sliding, so you can clearly see whenever you put a screw inside one hole, that screw not just rotate, it also moves in and out depending on in which direction you are performing the screwing operation. Okay, so if you are turning it in right direction, the screw will turn in that direction as well. It will move inside the hole. If you turn it in clockwise direction, the screw will come out, and it will also rotate in counterclockwise direction. Okay, so it will have both turning as well as sliding motion between them. And the last one is spherical pair. Okay, where we can clearly see we have one link which is in the form of a spear, and that is sitting or fixed inside the other link. Okay, um, so this is an particular example, maybe a joystick or um, a ball and socket joint is a particular example of spherical pair. Okay, so if spear is turning inside the fixed link, we call it as a spherical pair. I hope you understood these kinds of pairs. One is a lower pair. Lower pair means we have surface contact. Higher pair, we have a point or line contact. Closed pair means the links are held together mechanically. Unclosed pair, links are in contact because of the force of gravity. Sliding pair is having sliding motion. Then we have turning, rolling, screw, and helical pair, screw pair, and spherical pair, depending on the relative motion between the links. Okay, the name itself indicate in these cases what kind of motion they have between the links. Can I move towards next slide? Yeah. At this point, we should understand different types of joints. Okay, so if we are connecting two links, it is forming pair. Okay, or a joint, you can say in simple words. But it is not the case that we are just joining two links at a location. It can be possible that we are joining more than two links together. Okay, so depending on that, we have three types, or generally three types of joints: binary, quaternary, and binary, tertiary, and quaternary. Okay, so and so on. So, but these are the main ones. Okay, which are possible. The most important is a binary joint. Binary joint is that joint. Okay, name itself indicate that two links are joined together. Then to make a connection, then we call it as a binary joint. So in this particular figure, this particular joint, which is written as B, these are the examples of binary joints. Second one is tertiary or ternary joint. Let's call it as ternary joint. Ternary joint means three links are joined together at a point. So this 1, 2, 3, 4, 5, and 6 ternary um, joints are available in this example. Having a ternary joint is equivalent to having a two binary joints. Okay, so I would say it is considered equivalent to is considered equivalent to two binary joints. Okay. So for example, we have this particular link which is moving, and let's say these are two other links. This is link number one is a driving link, and these are driven by it. Let's say 2 and 3. If you fix 2, okay, uh, or let's say if you ignore these two, it's like 1 and 3 are connected to each other, and if you ignore 3, it's like 1 and 2 are connected to each other. Okay, so basically fixing one link um, can it can be imagined as like having two binary joints. So that is the reason we consider it as, if it is a tertiary joint, it is equivalent to like having two binary joints. Next one is quaternary joint. Name itself indicates that quaternary joint means we have four links joined at a connection. So this is an example, like I'll just make a square box here. Okay. Four links are connected at this particular location, and it is equivalent to three binary joints. Okay, name itself indicate what kind of joint is there. You just have to just count how many links are joined at that particular location. Okay, can I move towards next slide? Yeah. Degree of freedom. Okay, so if I take a rigid body in and if I remove all constraints, let's take for example a rigid body, and assume your pen which you are using now is a rigid body, and you put it in space. Okay, then that pen can either in x direction. Look at this figure. It can either translate in x direction, it can either translate in y direction, or it can either translate in z direction. Okay, so basically it will have three translation motion possible. Okay, and it can rotate about x-axis. Correct, that pen can rotate about x-axis. Try to imagine the pen rotating about x-axis. Okay, similarly that pen can rotate about or this, assume this box can rotate about x-axis or y-axis or z-axis. So basically any unconstrained rigid body will have 6 degrees of freedom. Okay, if you don't consider positive and negative, if you just consider it as let's say a particular direction irrespective of its sign, if the motion is in x direction, you have to assume it as one translation motion irrespective of positive and negative. Then we can say that there are 6 degrees of freedom unconstrained rigid body will have if you put it in the space. Do you agree? Okay, I am not considering all the directions like clockwise rotation, counterclockwise rotation, or motion in positive direction, motion is negative direction. If you consider that, then it will become 12. Okay, but in general, basically I'm considering here sliding motion in x, sliding motion in y, sliding motion in z, rotation about x, rotation about y, and rotation about z. Then I would say we have 6 degrees of freedom. Okay, so if I give you a pair, okay, and if I ask you to calculate the degrees of freedom of that pair, then how you will calculate, that is a question. Okay, so degrees of freedoms, degree of freedom uh, for a pair, of a pair is defined as number of independent relative motion okay a pair can have. Okay, the motion can be either translatory or rotatory. Okay, so degrees of freedom can be calculated by formula 6 minus number of constraints. Okay, number of constraint means if let's say for that pair um, so if I take the example which I have shown previously, try to imagine that example, a um, square prism, the motion of square prism inside a square hole. How many degrees of freedom you can expect there? I'll repeat the question. Yes, correct. Yeah, most of you answered it. It's one because um, all other motions we are constraining. Okay, we made sure that if you put a square prism, okay, or a square cross-section rod inside a square hole, it cannot rotate. Okay, it cannot rotate. It can just translate. Okay, and it can translate only in the direction on in about the axis of the hole. It cannot translate in other directions also. So only one translatory motion is possible. The other two the other two translatory motions are constrained, and rotatory motion is also constrained. So number of constraint in that case would be 5, and the degree of freedom hence is 1. Okay, so I'll go to the previous slide. Yeah, here yeah, so in this particular example, this is what I was explaining to you. Here the degree of freedom is 1. Okay, but I give you, if I give you this particular example, incompletely constant motion, we have, let's say, a circular rod which is uh, sliding in a circular cross section hole. Can you tell me how many degrees of freedom we have here? We have 2 degrees of freedom, correct? Because um, yeah, you answered it correctly, because we have constrained 4 degrees of freedom. We made clear that this rod cannot slide in y direction and z direction. If you assume this as x direction, it can just slide in x direction, and it can rotate about x direction, but it cannot rotate about y and z direction. Okay, hence you are constraining the or motion in the 4 directions basically. Okay, so basically number of restraints are 4, hence degrees of freedom is 6 minus 4, which is equal to 2. Okay, I'll come back to the original slide. So number of restraint means or number of constraints or restraints, you can say. Okay, the meaning of it is the number of directions in which you are constraining the motion. Okay, I hope it is clear to you. Yeah. Another definition which we should know. Can I move towards next slide? Have you written this? Yeah. Yeah. The next point I would like to start is linkage, mechanism, and structure. We should know the definition or the difference between these all. When we say it has a linkage, when we say it has a mechanism, and when we say it has a structure, things are more or less same with a slight difference. Okay, what is linkage? Linkage is obtained by one or more links of a kinematic chain fixed to the ground. Okay, so if we, so basically a chain, or let's see, if you take a link, if you connect the links, you can make a kinematic chain. So for example, this 1 link, 2 link, 3 link, and 4 link, this is your kinematic chain. Okay. And if one of the link you are fixing to the ground, fixed to the ground, then you call it as a linkage. You call it as a linkage. Okay. And if motion of any of the movable link results in the defined motion of other, okay, so for example, let's say take a slider crank mechanism. Okay. The motion of this crank, okay, depending on whatever is the motion of the crank, a definite motion of other links is there. Okay. So we can clearly say if the crank angle is 45 at, let's say, this 45 degree, the position of piston will be, let's say, x. If crank angle goes to 90 degree, the position will change to some, let's say, x minus 2, for example. Okay. If position of piston comes to 180 degree, then it is x minus 4, and so on. Okay. What I was trying to explain you is, like, if motion of any of the link results in the definite motion of the others, then you call it as a then that particular linkage is called as a mechanism. Okay. So basically a definite motion, relative definite motion. Okay. And what is the structure? Basically, if one of the link of the redundant chain is fixed, then that is called as a structure, basically, or locked system. Structure is nothing but a locked system. Structure is nothing but a locked system. So basically, it is a chain. You're making it with a combination of, let's say, different links, but ultimately it's not moving. Okay. It is getting locked because you have fixed, let's say, one of the links, and it making the system redundant and unable to move. In that case, that kind of system, you can either call it as structure or locked system. Okay. So what will be the degree of freedom of structure or locked system? Can you tell me what is degree of freedom in this case? 0. Correct. Because it's a locked structure, we cannot have any motion. Yeah. So whenever you are calculating degrees of freedom, if you come across 0 value, you have to understand that it is a locked structure, or you can call it as a structure, or it is a locked system. In some cases, it is also possible that you will get a degree of freedom negative. Okay. You know what is degree of freedom positive? We have studied examples where we have 1, 2, 6 degrees of freedoms also. But what is meaning of negative degree of freedom? It will also not make any sense. You can call it as a superstructure. So um, it means it is same as that, like we cannot have any possible motion here in this case also. Okay. This is, you can call it as a superstructure. So basically, it's like a locked system, but again we are like putting more constraint on it, on top of it. Okay. So which results in giving you the negative degrees of freedom. We know that degree of freedom is 6 minus number of constraint. If you put 6 constraint, your degree of freedom will become 0. Okay. But if you increase the constraint again and again on top of it, which will result in a negative degree of freedom, gives you the but that is also the meaning that it is a kind of lock system, and the name used for it is superstructure. Okay. um, yeah, then at this point we should know how we will calculate the degrees of freedom. That is the main question now. Okay, so if a mechanism is given to you, you should be able to identify what are the degrees of freedoms of that mechanism. Okay, so let's start with the general concept. As I already told, there are six degrees of freedom a rigid body can have. So considering that basics, let's say for example, in a particular mechanism we have n number of links. Okay, and then degrees of freedom are let's say defined with f, which is equal to 6 times n minus 1. Okay, minus 5 times p1 minus 4 times p2 minus 3 times p3 minus 2 times p4 minus p5. What is this? Let's try to understand. So in a mechanism, if you see how many links are there, in kinematic chain we are fixing one link. Okay, so basically in mechanism also we are fixing one link, because if it is a mechanism, it has to be a linkage first, right? And in order to become a linkage, one of the link you have to fix to the ground. So number of movable links are n minus 1. Okay, that's why 6 times n minus 1 is written here. If n is the total number of links in the mechanism, n minus 1 are the movable links, number of movable links. Okay, n minus 1 is total number of movable links in the mechanism. Okay, and that's why I'm writing now it is 6 times n minus 1, because number of degrees of freedom of n minus 1 links will be 6 times n minus 1, which that's why the first term is written it like this. And so there are, let's say in the mechanism there can be a pair um, with 1 degree of freedom, there can be a pair with a 2 degree of freedom, there can be a pair with a 3 degree of freedom, and so on till 5 degrees of freedom. Okay, so p1 p2 p3 are nothing but the number of pairs. What is p1? P1 is number of pairs having 1 degree of freedom. So what is p2? Number of pairs having 2 degree of freedom. And similarly, p5 is number of degrees uh, or basically number of pairs having 5 degrees of freedom. Okay, so each pair, um, let's say if it is 1 degree of freedom pair, how many constraint it will put? Can you tell me? Yes, it will put the 5 constraint, number of pairs with 1 degree of freedom. So each pair will put 5 constraints on it. Okay, because more the number of degrees of freedom, less the constraints will be there. More the constraint, less the degree of freedom. So if degree of freedom is 1, it means constraints are 5. Okay, so that's why 5 constraints you are subtracting from it. 5 times p1. Okay, 4 times p2. So 2 degree of freedom pairs means there are it is imposing 4 constraints. So that's why 4 into p2 is written here. And in the same way, p5 stands for number of pairs with a 5 degree of freedom. 5 degree of freedom means only one constraint. That's why we are multiplying p5 with 1. Okay, I hope you got this equation number 1. So this is in 3 dimension. In our syllabus, our focus is only in plane mechanism. Okay, not in 3 dimension mechanism. Plane mechanism means which are like we can draw on a plane of paper in a 2 dimension. So in 2 dimension, how this equation will look like? F can be written as 3 times n minus 1 minus 2 times p1 minus p2, because In 3 dimension, you have rotation in x direction. Sorry, you have translation in x direction, y direction, and z direction. But in 2 dimension, you have translation only in x and y. So that one translatory motion is gone. One translation is gone. Okay. Translation in z direction is gone. Okay. And rotation about x axis and y axis also gone. In 2 dimension, body can just rotate about z axis. Okay. About the axis which is perpendicular to the plane of paper. So basically, two rotation um, two rotational motions are gone. So that is why only 3 are remain out of 6, and that is the reason for 2 dimension or a plane mechanism, 2D or plane mechanism, I would say. I should write this formula, which is given by equation number 2. Is it clear till this? If you have any doubt, feel free to ask. Yeah. So what is n minus 1 is number of movable links. 3 is degrees of freedom a plane mechanism can have. So 3 into n minus 1 minus 2 times p1 minus p2. P1 means number of pairs with 1 degree of freedom, and p2 means number of pairs with a 2 degree of freedom. That's all. Okay. Yeah. Suppose so this equation is called as Grubler's criteria. So write down the name for this is Grubler's criteria. Okay. So in some cases they may ask you to match A and B, and um, in, let's say, on left hand side, if they put Grubler's criterion, then it is related to the degree of freedom of the mechanism. You should know. Okay. So this equation can further modified. Okay. Um, so for example, let me just make it more simplified in the next slide. I'll write it here. F is equal to 3 times n minus 1 minus 2 times p1 minus p2. Okay. So suppose if you consider a linkage or a mechanism with a single degree of freedom. Okay. If you consider a linkages with 1 degree of freedom. Linkages with 1 degree of freedom means we don't have a pair with 2 degrees of freedom. So p2 is 0. Number of pairs with having 2 degrees of freedom is 0. So this term will go. So basically f is equal to 3 times n minus 1 minus 2 times p1. Okay, this is the equation, and this is called as Kurzbach criteria. Okay, so Kurzbach criteria is a simplified version of Glauber's criteria applicable for the linkages with a single degree of freedom. Okay. So degree of freedom, you can clearly see, is depending on the number of basically the elements or the links in the mechanism, and number of pairs with single degree of freedom. Do you agree? This will define the degree of freedom. So if I want to make a single degree of freedom system or single degree of freedom mechanism, okay, so let's consider that I want to make a 1 degree of freedom mechanism. Okay, for 1 degree of freedom, what is the relationship which we'll get in terms of number of links and number of pairs, that I would like to explain you here. 1 is equal to 3 times n minus 1 minus 2 times p1 you will get. So it is 3n minus 3 minus 2 times p1. If you further simplify it, 2 times P1 will come on left hand side. 2P1 is equal to 3n minus 4. Okay. So number of pairs and links are related like this. So if n is equal to 4, what is P? P1 is equal to 3 into 4 is 12, 12 minus 4 is 8, 8 by 2 is 4. So basically, if 4 links, it will make 4 pairs with 1 degree of freedom. If n is equal to 6, okay, then number of, in first case, number of links and number of pairs are same, okay, but now you are increasing links to 6. What will happen? If you increase to 6, 6 into 3, 18 minus 4, you'll get 7. Yes. Okay. P1 is equal to 7. And if you similarly calculate it for 8, how much you'll get? P1 you should get as 9. Okay. Why I'm considering only 4, 6, and 8? Why not n is equal to 5 and 7? Okay. Oh, yeah, I think it's 10. Right. Correct. Here, correct. It is 10. Um, can you tell me why I'm not considering n is equal to 5 or 7? If you consider n is equal to 5, what will happen? 3 into 5, 15 minus 4 is 11 by 2. You will not get any whole number, right? So P1 and n needs to be like a whole number. Okay. And it is possible only when you have a n equal to a even number. Okay. So that's why I'm considering only the even numbers here. And what observation you can make from this is, as you increase the number of links after 4, okay, the number of excess pairs goes on increasing. So in case of 4 links, you have 4 pairs, but in case of 6 links, we have 7 pairs. And in case of 8 links, we have 10 pairs. So ultimately, what is happening is the number of turning pairs will go on increasing as you increase the number of pairs in case of one degree of freedom mechanisms. Okay, so this is the conclusion which you can make. So 2 conclusions we made here. One is for this will satisfy only n is even, if n is even. Okay, and if n is even, it will give to the whole numbers of n and p1. Okay, and second conclusion is, as n increases, okay, or basically as you increase the number of links, turning pair excess turning pairs will increase. So here we have 1 excess pair, here we have 0 excess pairs, 1 excess pairs, here we have 2 excess pairs. Okay, as n increasing, excess pair will also increase. The 2 conclusions which we can make out of it. Is it clear till this? Okay. There is one more relationship we have for calculating the degrees of freedom. Okay. Um, it is a little bit different from the what we have studied now. So write down these following empirical formulas, which are also helpful in some cases to calculate the degrees of freedom and the number of pairs with a 1 degree of freedom. So F is equal to n minus 2l plus 1. Okay, and P is equal to Okay, n plus L minus 1. P1, sorry. What is F here? F is the degree of freedom, we know. What is N? N also we know, number of links. The only different variable here is L, and it is called as number of loops. Okay, number of loops in a linkage. Okay, so for example, if I give you basically a single, let's say this kind of mechanism. In this particular mechanism, we have let's say only one loop. If I make it more complicated, for example, mm,
Sir, can we use when there was higher pairs also for this?
see, whenever you have higher pairs, let's say P2, P3, you better try to convert into a binary pair, okay? Because you remember said you like if we have uh, ternary pair or quaternary joint, basically it is equivalent to two binary and it is equivalent to uh, three binary. So you can convert it like this and then put it into this formula. Is it clear? You can still use
Sir, means we are not here in degree of freedom. We are not bothered about the joints, no, sir. There was
no,
loops and
no,
number of links. In this concept, sir, I'm asking, not the before degree of
ah,
freedom.
okay. In this case, yeah. In this case, um, we are we are taking the concept of loops in order to calculate P1 and F. Yeah. So in this case, we can have, let's say, tertiary or quaternary joints. Okay, ternary and quaternary joints. Uh, but that is the one which helps us to make the loops. Okay. Um, if you look into the examples, I'll give you examples when we solve some questions. Okay, there that time you will understand that basically the loops are formed because of these things only. Okay, if I take a, let's say, uh, a link with uh, three possible joints. Okay, a quaternary link if I take. Okay, and or let's say a ternary link if I take, and also if I make more joints, for example, um, binary let's say, or binary joint or a tertiary joint, ultimately it will reflect it into the loops. Okay, so loops are getting created because of this. Or if just we have simple, let's say, a single diagram, in this case there is just single loop. But if I want to make more and more loops, what I have to do, I have to make use of the links which are with, let's say, tertiary link or quaternary link. If I don't do that, what will happen? Let's say if I just put one more link here, the mechanism, in this mechanism, the inner link will be is a redundant link. It's like not useful. The mechanism still will work as it is. But if you use a let's say a ternary link or quaternary links and make the pairs with a more degrees of freedom, okay, or basically a ternary joint or a quaternary joint, ultimately it will create more loops. Okay, and that's how we are indirectly considering it in calculating the number of pairs and uh, degrees of freedom. So basically this P1 will help you to calculate the number of pairs with 1 degree of freedom. Okay, I'm not telling you that this formula will give you the number of pairs with a 2 degree of freedom and 3 degrees of freedom. It will give you the total number of pairs with a 1 degree of freedom. So there can be a pair with a 2 degree of freedom, but in this calculation they will um, um, they will just convert it into a 1 degree of freedom pair. Are you getting? Hello? Hello? Yeah. See, in binary joint, what I said is binary versus ternary joint. Ternary joint is equivalent to two binary joints, right? So, um, so basically, the similar approach is used here. I'm This formula will give us like only number of effective number of p1. It will not give us, um, let's say, the number of joints or number of pairs with 2 degrees of freedom and 3 degrees of freedom, even if they are in the mechanism. Okay, it will just give us the effective number of p1. Yep. I hope the things will be more clear when we solve questions on it. So yes, next point which we should know is 4-bar chain. Okay, so as if now we have all information which is needed to understand the different mechanisms. Okay, we know the basics. We know what is meant by link, what is meant by pair, what kind of different pairs are there, um, what is degree of freedom, what is constraints and all. So it's time to discuss more about uh, the different mechanisms now. Okay, and let's start with the simple 4-bar chain first. Basically, chain is nothing but combination. Uh, Dynamic chain is like if you just connect the links together, it forms a chain. And if you connect four uh, links, if you connect with each other, it becomes a plain kinematic chain. Okay, 4-bar chain. It is possible only when basically, for example, look into this particular diagram. A, B, C, D. These are the different 4 links. Okay, so if one link D, if it is bigger than rest of the 3 links, then you cannot basically make a joint. Okay, so if D is greater than sum of A plus B plus C, then in that case you cannot make this chain. Okay, so in order to make this chain, this condition should not, this should not be the case. Okay, basically D should be less than A plus B plus C, then at least you can make a joint. Okay, then later we'll see whether it will make any mechanism or not, what kind of mechanism we'll get. But the basic should be that in order to have this linkage ready, okay, as we are fixing the D, I will call it as the linkage. In order to have it a linkage, the length of D, because D is the largest link in this, okay, has to be more than the sorry, it should not be more than the sum of lengths of A plus B plus C. Okay, otherwise linkage will not exist. Yeah, so in case of 4-bar chain, there are some terminologies, okay, which we should know. For example, a crank, a coupler, and let's say lever, or you can call it as a rocker also. Okay, these are the general terminologies which we use whenever we talk about the 4-bar chain. What is crank? Whichever link which makes the complete revolution. Okay, if any link is there in the system and that is able to make the complete revolution, we call it as a crank. Okay, is it clear? Crank means the one which performs the complete rotation. What is coupler? Coupler is a link opposite to the fixed link. link opposite to the fixed link. And what is lever or rocker? So basically the remaining fourth link. So fixed link is, let's say this is a link in this particular example. Okay, for let's assume this example, okay, a random example, and assume that this is able to make a complete revolution. This is link number 1, link number 2, 3 and 4. So in this case, link number 2 is a crank because it is able to do the complete rotation. Link number 3 is, you can say, as a coupler, which is joining link 2 and 4, and link 4 is just oscillating, okay, or you can call it as a lever because it is just oscillating from one position to other depending on the rotation of the crank. Okay, so here the last link number 4, you can call it as a rocker or lever because it is oscillating. It can be crank also, okay, we'll see later. But for example, if any in case of a link, in any linkage, if the link is oscillating, okay, then we can call it as a lever or rocker. Okay, so if I use the terms now, crank, coupler, rocker, you should know what I'm talking about. Okay, is it clear till this? So take this particular example. In this diagram, I have shown one simple diagram where D is like, if you look into this diagram, D looks to be a smallest link here, correct, in this linkage. And if I move this A here, if I rotate this link A counterclockwise, this is how I will get. Okay, this is how our position of linkage will look like. Okay, D link is here, A link we made it in the, let's say, same direction of D. Okay, so basically what we can understood from it is D can B can basically come here. Okay, in other case, what I'm doing, let's say I'm bringing this C link horizontal, and what I can see here is now we could able to bring this C link in the direction of D link. Okay, on the same line, basically we can coincide them. Why we are able to make it like this? Because sum of D plus C is less than A plus B. Okay, sum of D plus C is less than A plus B, and the first case we were able to bring this A in the same line as that of D because sum of A plus D is less than B plus C. Okay, that is the reason we were able to bring this link A in the direction of, or in the same line that of D. Now think, for example, if let's say if this link A, okay, I would say here, whether it is possible if A plus D is greater than B plus C. Sorry, A plus B is greater than, no, A plus D is greater than B plus C. In this case, whether this figure is possible or not, can you tell me? It's not possible. In the same case, in this case also, basically if D plus C, if it is greater than A plus B, this figure is not possible. You cannot basically coincide them. Okay, so this is one learning from these figures which we are getting now. So let's try to make some conclusions out of it. Okay, so when we can say that let's say link can rotate. So if I'm able to bring this A down, it means I'm able to completely rotate this A. Okay, there is a chance that A can have a complete rotation. Okay, So it's time to make some conclusions here. I'll go to the next slide, and we'll try to understand some conclusions. So try to understand the same figure here. Okay, let's take this same figure. Try to understand, or we are making conclusion on this figure itself. So assuming that D is the smallest link, okay, D is the shortest link, um, and we'll see if we fix what conclusions we can make out of it. Okay. Yeah. So for example, in this case, let's start with the fixing link A. Okay, link number A. So what I'm saying is, if link adjacent to the shortest link is fixed, okay, if any link adjacent to the shortest link is fixed, what we can make conclusion out of it? In that case, obviously, D will gonna make a full rotation, correct? So D can have a full revolution. So we can call D as a crank, and the opposite to D, which is B, will be just rock, okay, and we can call it as a rocker. Okay, let me just try to explain through one diagram here. How the diagram was. Okay, so somewhat like this was the diagram. This is A, you are fixing, for example, B, C, and D. Okay, this is the first scenario in the yeah. Okay, we will consider all the scenarios. Okay, let's consider in this scenario, what I'm doing is a link adjacent to D link is fixed. So and to shortest link is fixed. Okay, then basically D will act as a crank. Okay, and the link opposite to D will rock. Okay, and C is a coupler here. Okay, and so rather than using D, I would say crank will be shortest link, and rocker will be the opposite to the shortest link. Okay, and the coupler will be the joining link in between crank and rocker. Okay, I'm using more generalized term because the same thing will happen if I just fix link C. Okay, so if not just A, if even if I let's say fix the link adjacent to D, which is C in this case now, in that case again the D will is the smallest link, it will act as a crank, and the opposite to it is B, which will rock or oscillate. Okay, and in between we have a link which is A in this case will act as a coupler. Okay, and so the mechanism is crank rocker mechanism or crank lever mechanism. Okay, crank rocker mechanism, you can say. Okay, so this is one situation, possible situation. I'll consolidate it afterwards. Um, suppose if I fix the link opposite to the shortest link, what will happen? Think on it. Okay, if you're fixing this, what will happen? Then basically this small link is acting as a coupler. Okay, and ultimately what we can clearly see, yeah, both A here and C here will just oscillate, right? So it's a oscillating converter, or oscillating converter, or you can call it as a rocker mechanism. Okay, rocker mechanism, double rocker mechanism, you can say. Okay, so this, and what will happen if I fix the shortest link, which was the initial case? Can anyone tell me what will happen if you put the shortest, if you fix the shortest link is fixed? And if I tell you that sum of the shortest and longest link is less than other two, then the mechanism which you will get is, anyone will get double crank. Yes, crank mechanism, you can say. Okay, crank mechanism. So this you can conclude when we have already studied this. We can say that whenever this is the smallest link, so this basically constraint I have kept, right? Then only you can make sure that these opposite links can fully rotate, and we will get a double crank mechanism. So these 3 points you should know. So in general, there are two class of linkages, class 1 and class 2. I will consolidate here. Class 1 linkage is like sum of the lengths of largest plus shortest. Okay, sum of the lengths of longest or largest, let's call it as the longest. Okay, if longest link plus shortest link, if this length is less than other two, sum of other two, then you can call it as a class 1 type of 4-bar chain. Okay, if it is class 2 type of 4-bar chain, then largest plus shortest is greater than sum of other two. And the special case, the third case is like type 3, you can say, or class 3 is largest plus shortest link is equal to the sum of other two. So can you tell me in this second case what kind of mechanism we will get if length of largest plus shortest is greater than sum of other two? Look at these cases. This is shortest, okay, and maybe let's say in this case largest is C. So D plus C, if it is greater than other two, what kind of mechanism I will expect? In this diagram, let's assume that D is the shortest, okay, and C is the longest, okay. Can you tell me if longest plus shortest is greater than sum of other two, what kind of mechanism you will expect? Anyone? Try to imagine. Can I bring this to here horizontally? Yes or no? No. Then both link number A and link number C can just oscillate. So you will, if this is the case, if in any mechanism, shortest link, sorry, largest and shortest length of the largest and shortest link, if it is greater than sum of other two, you will end up with a double rocker mechanism. If you fix any link here, not just shortest link, okay, if you fix any link, okay, you will always get a rocker mechanism. Okay. And what about the first class number 1? I have already explained you for that. In class number 1, depending on which link you are fixing, things will vary. If shortest link is fixed, crank mechanism you will get. Okay. If link opposite to the shortest link is fixed, you will get a rocker mechanism. And what is triple rocker? I didn't get your point.
Means all links, all unfixed links was rockers only, sir.
No, so basically the coupler is the one which is connecting input and output
It was
points. So
also
for example,
there
so if you are fixing this, okay, so this is your
in
input
class
link, okay,
in
this is your input link and this is your output link. And so whatever motion you are giving to link number A, ultimately you'll get some different motion in B, in C, and B is just a coupling between these two. Okay, so the name of the mechanism is based on the motion of A and C only, not on the B. So that's why the terminology rocker, crank, crank are used. Is it clear?
yes, sir, yes.
Yeah. So I hope it is clear that class 2 we always get a rocker mechanism. It is a class 1. We will either have depending on the link which we are fixing, we'll have either crank rocker mechanism, rocker mechanism, or crank mechanism. Okay, so these three are under class 1, but depending on which link we are fixing. And the class 3, which is like sum of largest and shortest link is equal to sum of other two. These are the special cases. Okay, these are some special cases. So let's see some examples for this special case in the second slide. I have shown you here a coupled wheel of locomotive. Coupled wheels of locomotive. So how we have joined them? We have joined them with the links A, B, C, D. D link is fixed here. So basically it's like a parallelogram. Length of B is equal to D and length of A is equal to C. So in that case, obviously, sum of shortest link plus largest link is longest link will be sum of other two. Correct? So in this case, in this particular application, we are getting a crank mechanism, both because we are fixing the largest link here. Link A as well as C will rotate. Okay. Whenever the sum of the lengths of largest and shortest links are equal, we have to look basically which links they are fixing, and on that we have to make some conclusions. Okay, so this second example which I have shown here is deltoid. Okay, in first example, coupled wheels of locomotive, you can clearly see opposite links are of same length, whereas in deltoid adjacent lengths are of same. So length of A is equal to D here and length of B is equal to C. Okay, adjacent lengths are same. So in this case, depending on which side you are fixing, your mechanism will change. So for example, here if I fix let's say smallest let's say a smallest side, which is D, what will happen if you are fixing D? A can come here down okay, because A plus D is very, very less than B plus C. So ultimately what you will do is you will end up with a double crank mechanism. Okay, so in this case you will get a double crank. Okay, whereas in second case, what is going to happen? If the longer link is fixed, longer link in the sense either so here C or B, in this case let's call, we have inverted it and this is the longest link which we are fixing here. In this case we have one crank and another one will be the rocker, crank rocker. Okay, so look at this example, um, how the things are changing. I'll use the laser pointer to explain. So suppose we have B point which is rotating because AB is a crank. If you rotate it like this, what is going to happen? This link C, that is B to C, will come down, okay, to C double dash and then go up. Okay, so basically it is oscillating in this, and it is not taking complete revolution. That's why the output link is a rocker and input link is a crank. That's why we will get a crank rocker mechanism. Okay, so from exam point of view, these things are very important. Whenever you get a question, try to check the lengths, whether lengths are given to the links or not. If lengths are given, check first whether input link, sum of input link and output link is sum of shortest and longest is less than other two or not. If it is less than other two, well and good, you can just check which link is fixed and on that we can do the conclusion. If it is greater than the sum of other two, it is rocker mechanism irrespective of which link you are fixing. Okay, and in class 3 these are the two possible cases: either opposite sides are fixed, or the adjacent sides, opposite sides are equal, or the adjacent sides are equal. And I have already explained these two. So in first case you may end up with a crank mechanism, and in second case you may either will end up with a crank or crank rocker, depending on which side you are fixing. Okay, so the main kind of questions which you can expect from the 4-bar chain is find the type of mechanism you will get. Okay, I hope it is clear till this. Any doubt? So we have a couple of more points left in this chapter. We have to understand some more points here, like mechanical advantage, transmission angle, and we also have to study slider crank chain and double slider crank chain and its inversions. So there are some more points to be covered in this chapter before we just jump on velocity and acceleration calculation. Okay, so I think we are at the end of our session now. If you have any questions, feel free to ask. Otherwise, we will end our session here and continue it in the next class. Okay. If no doubts, then we will end our session here. Thank you all for joining the class, and let's meet again in the next class. Thank you. Bye. Have a
You are
good Sunday.
currently the only person in this conference.